Now we move to the group of fine particles. Okay, so the fine particles. Remember, the idea here is that we're trying to understand, or we're trying to characterize the soil based on the properties that contribute to their behavior. So for coarse-grained soil, very important to realize, let me go back, that the grain size distribution, particularly the range of sizes that make the soil, is are the characteristics that control the behavior of the soil, and the properties, the strength and the stiffness, which is of most interest to us. Okay? So the fabric is controlled by the range of sizes in the soil, if the soil is coarse. Okay, this is for coarse particles actually. Alright. Now for fine-grained particles, we already talked about this, and we said, look, the fabric is controlled by the water present and the chemistry of the fluid, which is the water. Okay? So if the water is acidic, for example, the fine-grained soil that is touching that water, let's say, or that water is part of that soil, if that water is acidic, the soil assembles in a different fabric than if the water is basic, okay, which is not acidic. So you can read more about that in the book, etc. But the most important thing really is that you understand that the water chemistry plays a role in the fabric. For this course, which is the introductory course to geotech, we center our attention on the water content. Not on the water chemistry. We understand that water chemistry is important, but we center more on the amount of water present in the soil. Okay? And so we assess the behavior of fine-grained soils in the presence of water. Now, remember the Emax and Emin for coarse-grained soils? These are extremes, or we can say they are limits. We also have limits for fine-grained soils, but instead of E's, that is void ratios, those are for coarse, we use W's, water contents. Okay? There are two E's, Emax and Emin, that are relevant for coarse, and there are two W's, they are here, that are relevant for fine. They dictate the limits that are possible. In this case is what is possible. This case is a characterization of plasticity, as we will learn in this slide. Okay, so these two limits that are defined here, those two W's, this is a W and this is another W. Sometimes this is called WL and this is sometimes called WP. Liquid limit, plastic limit. Okay, they are W's. Just like for coarse-grained soil, Emax and Emin are E's, void ratios. Okay, these limits are called Atterberg limits because Atterberg was the one that started using this these water contents as characteristic behavior water contents. Okay, so as you can see here, the definition is the Atterberg limits are water contents at critical levels of soil strength for remolded soil specimens. Okay, so what does that mean? Well, that means that these limits are associated to soil that has been remolded. Remolded means that it has been disturbed in the lab. So what we do, in fact, when we determine these limits, these two, is that we take the soil and we mix it with water, and we mix it with by hand or with a device. So we actually destroy any fabric that could have been present and locked there due to nature. Okay, so we take the soil and we completely, mix it with water, and then we mix it in the lab, and we just shear it to a high degree. So that's what it's called. That's what remolded means. Okay, so here's the deal. Instead of going directly to the definitions, I'd like to do a little thought experiment with you. So let's say that you have a cup. We have talked about this before, actually. You have a cup and you put in some dry, fine-grained soil. Remember, this is for fine-grained soil, huh? Okay. Then you know the mass of soil. I'm going to write here mass of solids, S, because S stands for the grains and this soil is dry. Okay? So S stands for solids, particles. So let's say that we add water and then we mix. What we're gonna get is probably something that looks like a Play-Doh, okay? If we determine the water content of that Play-Doh, we'll get water content number 1, okay? That is a low water content. Let's say that then we add more water and we mix. We might get the consistency of a, I don't know, maybe like a paste, like toothpaste, okay? In that case, the water content is a little bit higher. Let's call it mid, right? Because we have more water. Remember that the water content is the mass of water over the mass of solids. Okay? And then let's say that we add even more water and we measure the water content of the remaining of the soil, and we have basically a high water content. In this case, the soil may act like a milkshake. Okay, so Play-Doh, toothpaste, milkshake. 3 different animals, but you have the same soil. What you have varied here is the water content. This wouldn't happen for coarse grain soil. Okay, this would happen only for fine grain soil. I hope you can see that. Okay. So, what's the point of all this? Well, there is a water content somewhere, maybe in here, that marks the transition between a material that is plastic-like, okay, let's say, and a material that actually behaves like a fluid. So there's a water content beyond which the material acts like a fluid. It doesn't act like a soil anymore, really. It acts more like a fluid, okay? Which means that anything you place above it sinks, for example, into the material, provided, of course, that the density of what you put above the material is higher than the material, okay? So it's not like a floating, there's no floating type of mechanics here, okay? Now, that water content beyond which the soil acts like a fluid, it doesn't act like a soil anymore, that's called the liquid limit, okay? Which is that, which is in the slide, LL. We'll get to it in a second, okay? Now, there's a water content. Let's say this is water content 0, and that's just dry. So the water content is 0, right? That's the beginning of the experiment, when the cup is just full of dry, fine grain soil. Well, there is a transition, the plastic limit, which marks the boundary between what's called a plastic solid, okay, and a plastic and a brittle solid, okay? So plastic solid, brittle solid. So you can think of this transition as one where if you add enough water or more water than this water content, you'll get a material that starts acting like a very, let's say, stiff Play-Doh, okay? If you remove some water from that material, it starts acting brittle. That means there starts cracking, okay? For example, when you try to compress it with your hand, okay? That transition is called the plastic limit. And it is the water content below which the soil acts as a brittle solid, okay? So these 2 limits, or transitions, are the Atterberg limits, the ones that we use to classify soil later on, okay? Now, notice that although it is perfectly fine to compare these 2 water contents to Emin and Emax, for the, not because they're the same, but because Emin and Emax are limits for coarse grain soil, and WP or PL and WL or LL are limits for fine grain soil. That is fine, you can compare them that way, but it's important to realize that a soil can exist with a water content that is higher than the liquid limit, and with a water content that is lower than the plastic limit. So these are not like totalitarian extremes like Emin and Emax. a soil cannot exist with a void ratio higher than Emax, higher than its Emax, and it cannot exist with a void ratio lower than its Emin. That's a coarse grain soils, okay? But for the liquid limit and plastic limit, the limits for fine grain soil, this soil can exist with a water content higher than the liquid limit and with a water content lower than its plastic limit. Okay? So just make sure that you see the distinction between the limits for the coarse grain soil and the limits for fine grain soil. For coarse grain soil, there are void ratios. For fine grain soil, there are water contents. Okay? And that's what's shown here. Sorry. Liquid limit, the water content above which the soil acts like a fluid. Plastic limit, water content below which the soil acts like a brittle solid. Okay? So, what are the typical values for liquid limit? 0 to 100. Why 0? 0 means that there's no liquid limit. Okay? So it's kind of a weird thing to put 0 here. So let's say a little bit more than 0 to 100. Plastic limit, a little bit more than 0 to 40%. These are percentages. Notice this. Some soils can have a liquid limit that is up to 10, up to 10, which means 1,000%, right? Remember that 1,000% basically means 10 in decimal form. So look at this. There is a soil, or there are soils out there, where the mass of water over the mass of solids, that ratio, has to be 10 to 1. This is 10, right? 1,000% is equal to 10. 10 to 1. That soil, those specific soils, require a water content where the mass of water over the mass of solids is 10 to 1, so that they start acting like a fluid. So look at that. For example, if you take 1 gram of this certain material, okay, it's a clay, typically it's called the montmorillonite, okay, clay. You take 1 gram of montmorillonite and add 10 grams of water, that's when the montmorillonite is going to start flowing like a fluid. It's amazing. Okay, 10 to 1. It's a lot of water for a little bit of material just to make it act like a fluid. Okay? That material, montmorillonite, has the same characteristic for the case of the plastic limit. So 150%, this means 1.5, that is 1.5 to 1. So look, even though in that soil there is more water than solids, than particles, the material acts like a plastic or brittle solid. It's actually in between the brittle and plastic solid, right? Because that's the boundary. The plastic limit is the boundary, transition. But still, you can think of it acting as a solid, brittle or plastic or whatever, but there's more water than particles in it. Very interesting way in which the electrical forces manifest so that between grains, the electrical forces between grains manifest so that you can get a soil that acts like a solid, but it has more water than particles in it. Okay. More, of course, of that you can read, and of course, with more clarity, you can read in the book. This is a nice graphical way to show the limits, okay? And it's essentially, what I had here in a kind of messy format, right? 0, low water content, middle water content, high water content, and then the liquid limit is in here and plastic limit is in here. So this is of course nicer version of this. Here's the water content, right? Axis. Here's the plastic limit, here's the liquid limit. Okay? When the soil has a water content below the plastic limit, it's a brittle solid. If the soil has a water content above the liquid limit, it is a fluid. And if the water content falls between the plastic limit and the liquid limit, we call it a plastic solid. Okay, this is basically very clear. Again, remember that the Atterberg limits are the water contents. Okay, they are specific water contents that mark transitions. And because they are associated with water, of course, they are dependent on the chemistry of the fluid. Okay, so for example, if you have a soil taken to the lab and you are asked to determine with tests the liquid limit and the plastic limit, and you will do this in the laboratory course, you basically take water, use water to determine the liquid limit and the plastic limit. Okay, fine. So let's say that for your soil you determine the plastic limit to be 50 and the liquid limit to be 82%. Okay, fine. Now let's say that the next lab session comes in and they have the same type of soil, but instead of using water, let's say from the faucet, okay, which you used in your determination of these two parameters, let's say that they use water that was obtained from an unknown bucket in the laboratory of environmental engineering, okay, and let's say that that bucket actually has some chemicals in it, or that water, okay, some ions, unknown ions or whatever. Okay, they run the test on the same soil and they determine that the plastic limit is 62 and the liquid limit is 121. Okay, and that's fine, that could happen. So of importance here is that the liquid limit and the plastic limit are not only a function or dependent on the type of soil that is tested. Each soil has its liquid limit and its plastic limit, but they are dependent also on the water chemistry, okay, of that soil. So one should say that there is that each soil water mixture, okay, has a liquid limit and a plastic limit. Okay. All right. So make sure that you realize that the water chemistry affects these limits because it affects how particles assemble. And these limits are a manifestation, basically, or these limits here basically describe indirectly how the particles are assembling, that is the fabric of the soil, fine grained. Nobody talks about plastic limit and liquid limit of gravel or sand, okay? So don't make that mistake. Okay. Now, we have a definition here that is very important, and it is another parameter that emerges, okay, which is basically just liquid limit minus plastic limit. It's just the difference. It's called the plasticity index, and it tells you the range within which the soil exhibits plastic behavior. Okay, so it's this range right here. So the difference between this and this gives you a number, and that number is the range, okay, within which the soil exhibits plastic solid behavior, let's call it, okay, or plastic behavior. So for this case, for this soil, the plasticity index is 121 minus 62, which is, this is right, so 59. That is the plasticity index. Okay, so that is the way that we calculate the plasticity index. Later on, you'll see that you will need this plasticity index to classify the soil. So essentially, this lecture this is number 5. This lecture is actually a background for the classification of soil, and of course, it has some of the physics and some of the relevant parameters for that. Sorry. Okay, next slide. Remember that for coarse grained soil, we had a parameter called the relative density, which basically gave us an indication of the status of the soil, density status or void ratio status, relative to the limits that that soil can have. That's for coarse grained soil, relative density. Well, for fine grained soil, we have the liquid limit and the plastic limit as the limits, and therefore we should be able to compare the plastic limit and the liquid limit to the in situ water content. Remember that the plastic limit and the liquid limit are water contents, okay? It's sometimes many students don't fail to realize that that the plastic limit is a water content and the liquid limit is a water content, okay? For some reason, there's some confusion there. Maybe because they are not called W something, they're called PL. This is a water content. This is LL minus PL, right? The plasticity index. In any case, just make sure that you realize that the liquid limit and the plastic limit, both of them are water contents. So if we compare the water content in situ, that is the water content of the soil in the field, of a certain soil that we're interested in. In the field it has a water content because nature has deposited that soil and basically given that soil water in whatever way possible, so such that it has a specific water content in the field, okay? But we take that soil to the lab, we determine the liquid limit and the plastic limit by mixing it with different amounts of water, etc. You'll learn that in 463. And then we can compare those limits to the in situ water content. And here it is. The liquidity index is the in situ water content, determined in the field, of course, minus the plastic limit of the soil, determined in the lab, divided by the plasticity index, which is the liquid limit determined in the lab minus the plastic limit determined in the lab. Okay? So just like for relative density for coarse grain soil, we have a little axis here. Here's the liquidity index. And it basically mimics the axis in the previous slide, but it's normalized, as you can see. So if the liquidity index is 0, the soil is at the plastic limit. If the liquidity index is 1, the soil is at the liquid limit. If the liquidity index is larger than 1, then the soil in situ is acting like a fluid. Okay? So it may be like a swamp, very muddy swamp. Okay? If the soil has in situ has a liquidity index less than 0, then the soil is a brittle solid. So it may be like a crust, for example. Okay, like in the desert. Okay? But it doesn't have to be in the desert, it could be anywhere, just that in the desert is probably this is probably the case. Okay? And generally most of the time when we are not in extreme environments, the soil in situ is in the plastic regime. Okay? Which means that its liquidity index is between 0 and 1. That's typically what we encounter. Okay? And that's fine. All of them are fine. We can deal with all of them because that's what engineers are for. We deal with all the problems that we can possibly get. Okay, and the last slide is this one, and you have seen this one before. This is a very important slide, so I tend to, go back to it maybe 2 or 3 times during the course because it really tells us the story that we have to have in mind. Okay, soil behavior is controlled by fabric or packing. Here we have made a distinction between the word fabric and the word packing. They're really the same, but fabric is generally used for fine grain soil and packing is generally used for coarse grain soil. You can use fabric for both, that's fine. Okay? What is important is that you understand that fabric, the word fabric, it basically means the way in which particles are assembled, okay, one next to the other. The structure of the soil is like a structure, okay, like the structure of a building, okay. How the particles are assembled, that dictates the behavior, okay. So for fine grain soil, let's begin with coarse because we talked about those first. Coarse grain soil is sand and gravel, right? The fabric or packing is controlled by the grain size distribution and the particle shapes. Okay, we didn't talk much about particle shapes, but just so that you have this in mind, let's make let's just create some little drawings here. Let's say that you have a soil, a coarse grain soil where the particles are spherical. Okay, and they are the same size, just for the sake of an example. In this case, the particles can assemble in a way that is quite dense. Okay, so particles fall in between the crevices like in this fashion. This is called a tetrahedral packing of spheres. Okay. Clearly, particles in the world, particles of soil, are not spherical, perfect spheres, but some of them are actually quite rounded. Well, what happens if you have a particle, a soil that is made of particles that are like angular, like this? This is called angular shape, etc. Right? Anyway, these particles will never assemble in such a dense configuration. Okay, so these particles, the minimum void ratio that they can achieve, that this soil can achieve, is going to be larger than the minimum void ratio that this soil can achieve, because these particles are angular. It's hard for them to fit closely against each other, whereas these ones can, right? So particle shape definitely controls or controls, along with grain size distribution, the fabric of the soil, and in turn the fabric controls the behavior, the strength and the stiffness. Okay. Now, for fine grain soil, well, for coarse grain soil, because of the fact that grain size distribution and particle shapes control the fabric, we have E max and E min as the characteristic limits of state. Okay. Now, for fine grain soil, what controls the fabric is the water content, the amount of water in the soil, okay, and the water chemistry, as we discussed. Okay. Of relevance to this course is most important, I guess, for this course is the water content. Therefore, what we use for the limits for this type of soil, to characterize the limits, is the liquid limit, which is a water content, and the plastic limit, which is the other water content. Okay, the other characteristic extreme. Okay, we shouldn't call them extremes or limits actually, because they are not true limits. They are characteristic values that mark transitions in behavior. These ones. Okay, so remember, even though we are geotech engineers and we have a bunch of different soils, etc., there's actually a distinction between the coarse and the fine. It's like two different animals, and we have to deal with both of them. Okay? So, very important slide. Make sure that you sit there and stare at it for 10 minutes before going to sleep. Okay, so with this we finish the lecture on fine versus coarse. The next one is soil classification, where we're going to use the grain size distribution, we're going to use the liquid limit and the plastic limit, etc., to actually classify the soil based on its engineering behavior. Classify in a standard fashion. Okay?